Okay, so here's another problem for our equivalent force system that we've been doing. This one's really not as complicated as some of the examples we did earlier. It's a single distributed force, and you can see it's really trapezoidal. I don't remember the area of a trapezoid off the top of my head. Well, I know the area, but I don't remember the centroid very easily. So this is a classic problem where I think it's best to divide it into a triangle and a rectangle. So if you look at this rectangular area and then the triangular area. So the rectangular area, 2 kilonewtons per meter. And then of course the actual height of the triangle would only be 3 kilonewtons per meter. So that gives us all the information we really need to get started. So what's the equivalent force for the rectangle? Well, let me ask you this. Where do you think, I'll just kind of sketch it in. The equivalent force for the rectangle is here. I'll just call that, say, F1. So what is the value of F1? It's the area of the rectangle, which is base times height, which is 2 kilonewtons per meter times 6 meters. So it looks like it's just 12 kilonewtons. We're going to base everything from A. So what would be the distance from A to the center of the rectangle? I'll call that x bar 1. So what's the distance from A to the center of this rectangle? It's the midpoint, right? So what's the midpoint of 6? 3 meters. Now the triangular force, remember the centroid for that is over here towards the larger side. I'll call that F2. So what is the area under that part of the curve, F2? So a triangle is 1/2 base times height, so 1/2 base, 6 times height, 3. So that should be 1/2 base, 6 meters, times height, 3 kilonewtons per meter. So that's what, 9 kilonewtons? Mm-hmm. Now its distance from A, again, is, in this case, it would be 2/3 of the distance. 2/3 of 6 meters, 6 meters is 4 meters. Okay? So I've got the components. So what's my resultant force? It's just F1 plus F2, right? In this case, it would be 21 kilonewtons. And where is it located? Well, what we want to do is we want to make sure that the equivalent moment about A for these two forces is the same as the resultant. So I will sum moments about A, and I'll use my first two forces. So I'll have F1 times its distance plus F2 times its distance, and that has to be equal to what? The resultant force times its distance. So in this huge equation, the only thing we don't know is that value right there. So F1 is going to be 12 kilonewton times 3 meters. F2 is 9 kilonewtons times 4 meters. And that should be equal to our 21 kilonewton force times the distance from A to it. So what is that position?
3.43.
That was fast. That looks good to me. So now we know where it's located and what its value is. Now, in the problems that we'll probably start tomorrow, this will be the first step. We'll probably want to turn the distributed force system into a concentrated force and a location, and then we'll proceed to do the problem, whatever the problem might be. So this will be probably a first step in some more sophisticated problems that we'll start tomorrow. Any other questions? Okay.